Thank you very much, Nicolo, for the invitation. And yes, today I want to talk about recent work from March that a paper I wrote together with Ralf Blumhagen and Juying Wang. And to properly talk about the topic, which is dynamical cobordism, I should start with first introducing cobordism. So cobordism is a very powerful framework developed by mathematicians in the 1950s and then continuously throughout the 20th century. The idea is the following. So let's take two compact closed n-dimensional manifolds, M and N, and then we can define an equivalence relation, which is called cobordance, that if M and N can be connected by a higher dimensional, one-dimensional higher manifold, such that the boundary of this manifold, let's call it W, gives us the boundaries again, gives us the manifolds as its boundaries again, then we can call M and N cobordant. And actually, in physics terms, this means that we basically allow for topology changing processes between M and N. And we can now classify these kind of processes. We can these kind of cobordant equivalence classes. And if we additionally take the disjoint union into account, these cobordism classes form actually abelian groups. Now I sneakily introduced this denotes some kind of structure, which I did not specify here, which should be preserved on W, M, and N throughout the topology changing process. And this can encode very interesting physics. So in the context of string phenomenology, McNamara and Waffer pointed out that a non-vanishing cobordism group should be actually understood as a non-vanishing global symmetry. And due to the well-established conjecture that global symmetries should be absent in quantum gravity, this would imply that these kind of non-trivial cobordism groups, where now we need to introduce some kind of quantum gravity structure on top, should all be gone. So this means that from a physics standpoint, every manifold which is in this vanishing cobordism class has to have a manifold W which makes it disappear, basically. This is a so-called null-bordant manifold. All right, now, since we don't have a perfect description of what this quantum gravity structure should look like, we can take a step and look at interesting structures which encode interesting types of physics, for example, a spin structure, and we will see that their non-trivial cobordism groups will pop up, and we need to make it quantum gravity. So in the context of dynamical cobordism, we will mostly be concerned about breaking this global symmetry. And this is done by introducing a defect such that with this operation which lets this manifold M be cobordant to nothing again. So this kind of defect can be understood as some kind of brane, for example, in string theory. Okay, so far we've only talked about a topological obstruction, but in 21, the Spanish group extended the notion of cobordism to also include dynamical geometry topological obstruction. And specifically, they looked at a class of spacetimes which have singularities at a finite distance due to some running potential. And they interpreted this kind of finite distance geometry as a null-bordened configuration, as we just saw, because of a defect at the singularity. So this would be called some kind of end-of-the-world brane. All right, so occurring in string theory, but they share some common features, some scaling properties of the geometry close to the singularities. And in particular, it obtains an exponential scaling close to the singularity with a parameter delta, and this exponential scaling is with the distance in field space. The same is true for the Ricci scalar, the spacetime curvature, which also intriguingly shares the same coefficient in the exponential. Now, what about actually these end-of-the-world branes at these singularities? Are they actually solutions, local solutions of the equations of motions? And interestingly, in 2022, we showed that we can explicitly construct such end-of-the-world brane solutions in one very specific setup. So now the goal is to generalize this notion and look at a general parameter space and look up what kind of special features these end-of-the-world branes have and what we can learn about them. So we looked in particular at the so-called generalized Dudas-Mourad model, which introduces two general parameters, which is on one hand the tension lambda and the exponential coupling constant b. So this model is the parameter space of lambda and b also contains very important string theoretic examples. There's two examples I want to highlight specifically. There's the Sugimoto model, which is a non-supersymmetric orientifold of type 2b. So basically, this can be viewed as a twin theory to type 1 string theory, where instead of a stack of O9 minus plane and O9 minus plane and 32 D9 branes, we have an O9 plus plane and 32 anti-D9 branes, which manage to achieve a complete Tedbow cancellation. However, we introduce a non-trivial tension because those don't cancel, they are both positive. So this means that we introduce this non-trivial potential here, this running potential. And on the other hand, another example is massive type 2a, where we can view this zero form flux of this exponential coupling term. Now, the next thing to do is to actually solve the equations of motion. Because of this running potential, we don't have a maximally symmetric solution anymore, but we can compromise and we can find solutions with a warp geometry, which I demonstrated here in this metric. I will not give you all the details of the equations of motion, but what I want to highlight is the fact that with some kind of auxiliary function, one can simplify the equations of motions significantly, and one gets this very interesting differential equation where we see that we actually get a non-trivial parameter space for this exponential coupling parameter b, where the solutions change whether or not b is smaller or larger than this critical value. This means that we should divide the solutions in different regions and look at each of them specifically. All right, so moreover, we can calculate the space-time distance, and they have exactly the exponential scaling that we expected based on the notion of dynamical cobordism. And depending on the boundary we look at, delta is either given by some kind of mini value, which is this critical value that I introduced before, or if b is larger than the critical value, it actually has a more general delta, a larger one. So we have some kind of lower value for. And also for the Ricci scalar, the prefactor of the leading divergence can be calculated, and this is given by these very specific values that we can check whether or not our local end of the WebBrain solutions that we want to construct actually if they match them. Now here is a nice overview over all the possibilities that you can have. Here I want to highlight the 3 different regions. The epsilons indicate different choices of signs, but this doesn't matter too much. What I want to highlight is that if B, the absolute value of B, so the first or third region, end of the WorldBrain which has a scaling with this critical value, and on the other hand, we have this more general scaling. Whereas if B is smaller than a critical value, this kind of scaling seems to be fixed to this critical value. And B is not as general anymore, or delta is not as general anymore. All right, now to construct the neutral end of the WorldBrain solutions, we first started by making a neutral codimension 1 brain ansatz, which has again 2 open parameters, the tension and the exponential coupling. And we can again solve the geometry by some kind of warped ansatz. And immediately by consistency of the equations of motion, A is actually is restricted to the critical value that we saw before, which is already a very nice indication. The second open parameter, the tension of the brain, is fixed by the jump condition. We have to implement at 0 because the world has to end there. There's actually a nice subtlety here. So this C1 is an integration constant we get by solving the equations of motion. And depending on the choice of C1, depending on the sign of it, we get either positive or negative tension for the brain. We chose it to be negative because this would correspond to a solution where the singularity is slightly outside of the interval, outside of our world, basically. All right, now we can check whether or not we actually get the properties that we wanted to have. And it turns out, yes, we do. The space-time distance has precisely the scaling with the critical value of B. So this is very nice. The curvature not only has the required exponential scaling, here expressed in terms of delta, but also we can match the prefactor, which is a nice consistency check. So we have exactly the properties of an end of the WorldBrain, which I called, which I named like this before. And analogously, we get also the end of the WorldBrains on the right boundary. Very nice. However, what is missing is the mode. So I want to point out that in 10 dimensions, this coupling to the dilaton is depending on the sign, 3 or -3/2 phi. These appear to be unknown dilaton couplings, so they appear to describe new 9-dimensional. All right, now what about the other end of the WorldBrain? Well, let's use the string theory examples that we have as a guiding principle. In particular, massive type 2A. Why? Because massive type 2A is exactly in the regime that that we have the necessity to have these general end of the world branes. And specifically, as I pointed out before, the tension lambda there is given by the Romans mass or some kind of zero form flux. The idea here is that because our spacetime ends at a finite distance, this end of the world brane should be able to absorb the zero form flux. This means that our codimension 1 end of the world brane that we are looking for should couple magnetically to the zero form flux. This means that we need to introduce a charge end of the world brane ansatz and look for solutions there. So I highlighted the additional terms to the neutral ansatz. The geometry is basically the same, but we gain this additional dynamical field in C. Now, solving the equations of motions get us the exponential coupling of the brane and also the charge in terms of B. So B is unfixed as we require, and actually, which is nice, we get for a specific value of B, we get the neutral end of the world brane ansatz back, part of this more general ansatz. Moreover, the parameter space also includes a BPS case where the tension is equal to the charge. And I pointed this value out here. This will I will come back to this. Let's talk about the tension and the charge. They can be finite conditions, and in the end we get all the parameters fixed in terms of B, which is a good sign. Now, to finally check it, we need to again calculate the spacetime distance, and we get precisely the scaling with B close to the singularity, and scalar not only matches the scaling, the exponential scaling that we wanted, but also we get the right prefactor. A second thing we have to check is if this charge end of the world brane actually carries this constant magnetically dual zero form flux, and by calculating F tilde, we get that this gives us precisely just this constant value of mu. All right, so based on our results, we find that the following end of the world branes are actually needed to close off the geometry at the boundaries of this generalized Dudas-Mourad model. So for B, for example, an example would be the Sugimoto model. There are two neutral end of the world branes required at both boundaries at y = 0 and y to infinity. And for B larger than its critical value, we need one neutral and one charged end of the world brane, as for example is the case for massive type 2A. Moreover, massive type 2A has B equal to 5/2, which corresponds precisely to the BPS point I pointed out before of B in 10 dimensions. So we could check that in string frame, the corresponding action of this charged end of the world brane is precisely the O8 plane with negative tension, which confirms a proposal by the Spanish group in 2021, which is a very nice consistency check. All right. Finally, I want to point out some connections to several distance conjectures, namely close to this singularities where we go off to infinity in field space. We would expect a tower of masses coming down, and moreover, there was recently this proposal to sharpen the distance conjecture, that there should be an upper bound on the type of coefficient we can have in this mass. And combining that with our exponential scaling we get for the Ricci scalar, we get some kind of polynomial scaling of the masses in terms of the Ricci scalar with some coefficient which is given by the ratio of those two exponential coefficients. And since delta can never be smaller than its critical value, as we've seen, this is bounded by above by 1/2. This is very interesting since same polynomial scaling in the Sitter distance conjecture, but also we have an upper bound there, which comes from the Higuchi bound from the Sitter. It's also 1/2. So this is very interesting. However, I should point out that the boundary behavior in the dynamic cobordism picture is rather distinct from the Sitter distance conjecture. So not only is R going to infinity instead of 0, as in the Sitter distance conjecture, but also Sitter geometry close to the boundary, it's just positively curved. So this could either be a coincidence, or it could point to maybe a generalization of the Sitter distance conjecture. All right, so in our paper we investigated the parameter space of dynamical Mourad models as well as Blumhagen font models, but I didn't have time to go over the discussion there. The parameter space is we identified neutral and charged end of the word branes as the required defects by the Cobordism conjecture, including a BPS case, which has a topological charge. So this features some kind of supplementation of the topological Cobordism framework. So in the future, it would be very interesting to work out the precise mathematical framework which combines those two. And maybe the BPS case can serve as some kind of middle ground because we have a topological charge there that we can work with. Also, SO16 heterotic string has a value of B and the exponential coupling in the regime where we would expect charged end of the word branes, which is curious because there are not any charged branes known in the heterotic string, so this is an open question. And also would be interesting to work out higher codimension, which seems to be much more complicated. And the question is if solutions can be worked out and what the parameter space for that would look like. So with that, thank you very much.
Thank you, Christian, for the nice talk. So, other questions? Yes, please.
Hi, can you hear me?
Hi.
Hello,
Yeah.
Thanks a lot for the talk. I have just a doubt, probably you mentioned it, I just missed it, sorry if that's the case. I'm a bit confused about the bound on the delta coefficient, that you say that you always find delta bigger than these two square root d minus 1 over d minus 2,
Yes.
right?
Yes.
I'm a bit confused because at least according to this local dynamical cobordism analysis we did,
Yeah.
I think you can find any value of delta. It just depends on the exponential that you put in the potential and whether the potential is positive or negative. Is this something that has to do with like not only the local behavior, but saying that the solution should be global, or it's something that you observe in string theory?
I think this, I think we checked that this actually matches your results. I think you also find this lower value on delta. I think if you require that V is larger than 0 or something.
And so having a positive potential or a negative potential.
I think this is the requirement that we
Oh,
have here. I think
okay,
so.
you are requiring the potential to be
This would
positive.
completely change if, yeah.
Okay, perfect. Okay, thank you. Thanks.
Sure.
Yes, other questions?
Can you hear me, or is it the wrong microphone?
I can hear you. I don't know, Christian.
Yeah.
Try again. Can you hear me?
Yes.
Okay, yeah, perfect. I have a question, sorry, I probably missed it. So when you first stated your model without the resolvent of the end of the world brane, you had this exponential potential in the action. And then, yeah, precisely this, wait.
Yeah, here.
This one, yes, there's this exponential potential. And then when you had the model with the boundary, you had this e to the b phi term only on the boundary, but not in the bulk anymore. Is that true, or did I miss it?
Okay, so for the Dudas-Mourad model, this is the original model giving rise to the geometry, and then precisely for the end of the world brane ansatz, we of course want a codimension 1 brane coming from which is basically living at the boundary of the geometry that we found from the general Dudas-Mourad model. So this is the ansatz just for the end of the world brane.
Yeah, I would have expected the e to the A0 phi term to also be present in the bulk. Because now it's only present at the boundary, or am I reading this action wrong?
For the description of the end of the world brane, yes. I mean, this term is present at the boundary, yes.
But not in the bulk anymore, right?
No.
And I'm asking why this is not present in the bulk anymore.
Okay, I see. So this is just the local end of the world brane that we want to find as being responsible for this kind of boundary behavior. What you can also do alternatively, which I have not presented, is that you could go to the Dudas-Mourad model and implement the boundary conditions for these end of the world branes directly in the framework of just the bulk action. It's also possible.
I see. So you say it doesn't really matter if you do it in the bulk and then demand the proper boundary conditions, or you don't demand it in the bulk and then add this term for the end world brane.
Exactly. Yeah.
I see. Thank you.
So these are complementary pictures.
I see. Thank you.
Yes, last question maybe.
Yeah, sorry, can you hear me? Not so much, maybe
Very
now?
low volume, yeah.
Okay, I'll
That's better,
speak
yeah.
loudly. Okay, thanks so much for the talk. I had a question about something you said at the end. About how dimension objects are harder to solve, I guess, because of the boundary conditions and whatnot.
Yeah.
Why couldn't you just take the codimension 1 case and put it on a circle, you know, and say that the circle is small enough such that effectively you just have a codimension 2, a lower dimensional object?
Yeah, so codimension 2 works out fine. This is the Blumhagen font model I mentioned briefly. So yeah, there basically what you do is you basically start out with this kind of end of the world brane action. So this kind of localized object. This gives rise to then a different geometry which has codimension 2 objects. But going beyond that is much more complicated, because then, I mean, you have lots more warp factors and basically many dynamics you have to control. And this is tough to solve, but probably just tough to solve and not impossible.
And could you have obtained the codimension 2 brane by like compactifying a codimension 1 brane on a circle, or is it like intrinsically different?
it's a bit different. Interestingly, we don't find the charge case there. And for the whole parameter space, we only find these neutral end of the word brane objects. So it seems to be a bit different, yes.
Okay, thanks a lot. That helps.
Okay, so thank you all. Thank you, Huri, and thank you, Christian, for the nice talks.